Welcome, guys, to the very first lecture in my course on theory of partial differential equations. In the very first lecture, we are going to discuss some major results in function analysis. So if you have some sort of good background in analysis and measure theory, then these things will really be a piece of cake for you because I'm just going to quote the main results. I'm not going to discuss them in detail. But we are here to just quote them, and then later on we'll apply these results in the theory of partial differential equations whenever we need them. So it is not necessary to just grasp all the ideas, just have a look at these, try to understand, and just keep in your mind or just keep these somewhere that we are going to use these next in the subsequent theorems and chapters. So I have already gave you 3 reference books, and this material is really basic. So like you won't find this one in any of those 3 books because those 3 books are related to theory of partial differential equations. But in the very first lecture, I'm going to revise function analysis. And in the second lecture, I will revise measure theory. So let us do some major results in function analysis. So I'm assuming X to be a topological vector space, and in short, I denote it by TVS over R or the set of complex numbers. So you know very well that, okay, what do you mean by a vector space? There is some sort of algebraic structure that satisfies certain axioms. And by topological means, I can define some sort of topology on that vector space. So now I have a definition that what do you mean by a norm? A norm on topological vector space is a mapping which takes you from the vector space to the set of real numbers. So it's some sort of mapping. And let me denote the mapping with this symbol, which takes you from the topological vector space, and the output is going to be some sort of real number that has the following properties. So such that number one is the norm is always non-negative for all x to be from the vector space or the topological vector space. And number two, if I scale any vector in the topological vector space, it is same as scaling the norm by the factor mod of alpha, where alpha is a real number and this x is from this vector space X. And third property is what do we call triangle inequality. X plus y, the norm of x plus y is less than or equal to norm of x plus norm of y for all xy from the topological vector space. So this is how we define norm. So the next definition is normed vector space. So we define norm with the help of norm. I'm going to define normed vector space, also called normed linear space. I'm not going to write it. So L is for linear here, is a topological vector space. So a normed space is basically a topological vector space with a norm defined on it. So if it is some sort of norm, then we call it a normed vector space. So this is how we define a normed vector space. I can denote it with X along with some sort of norm defined over it. So then I have another definition. Which says that we have X to be normed linear space that we have already. We are going to define a mapping and define a mapping. And what is the mapping? It's some sort of mapping row which takes two elements from your normed linear space and gives you a real number. And one of the example of such a mapping is like the norm of difference between X and Y. So this is the map, what we call distance map as well, which gives you some sort of metric. Metric means how you can find out distances between 2 points in a given normed linear space. And with the help of metering, we can define what do you mean by open balls, which is some sort of like a special case of open sets. Yeah, it is some sort of things related to open sets. So these things are really crucial when we are going to discuss topology and discuss metric spaces. Okay, so let us do some sort of extension of normed spaces. So what do we call Banach space? So what is a Banach space? The simple definition is it's a complete normed linear space. So what is normed linear space? It is some sort of vector space with some norm defined over it. But if the space is complete, we call it a Banach space. Now the question is, what do you mean by complete? So let me write first thing that, okay, we'll write BS, and BS stands for Banach space. So complete means the space contains all of the limit points of all the sequences inside it. So contains all its limit points. It means if I take any sequence in the non-linear space, if the limit of the sequence belongs to the space, same space, then I call that space to be a complete space, and complete non-linear spaces are called Banach spaces. So like if I take any sequence that belongs to X or contain, it is contained in X because it has many elements. It is a set. Yeah, it's contained, not. So Xn converges to some X, and it implies that the limit X must be from the normed linear space. Hence, we call this space to be a complete space, and all the complete normed spaces are called Banach spaces. I have a definition. We say Banach space is separable if it contains a countable dense set. So we have some sort of notion of separability in Banach spaces. And one of these example that I'm going to put forward is the set of real numbers. It's a Banach space, and it is a separable Banach space. And what is the reason behind it? It contains Q. And what is Q? Q is one thing, Q is dense in R. And the second thing is Q is countable. And what do you mean by countable? Like, it is some sort of basic notion which is done in analysis, so it's not that much difficult. You can make some sort of isomorphism between Q and Z2. It means Z cross Z, there is some sort of uh, isomorphism existing between these sets. So the Z is countable set, you know very well. So Z cross Z is also countable, hence Q is going to be countable. But there is not some sort of exact isomorphism. Yeah, because there are some sort of repetitions in Z cross Z as well. But these things are going to be so much advanced and in depth, so we are not going to discuss these things. For an example, let us discuss space, which is space of continuous functions over -1 to 1. And it is some sort of functions which are from -1 to 1 mapped to R, and F is continuous. This is how we define this space. Now the question is this space a Banach space? First of all, for Banach space, we know we should have a norm in the elements in this space. So if you take any F in this space, the norm is going to be the maximum norm, because one thing is that the function is continuous. Maximum of the absolute value of x for all x from -1 to 1. So function is continuous and it is between -1 and 1. So there must be some sort of maximum value of the function if the function is continuous. Now there are two things. If the function is not continuous, then you cannot say anything about the maximum value. And if the domain is unbounded, again, it's going to be the problem. The function is continuous, but maybe at negative infinity or positive infinity, there's going to be some value which is not finite. So we can define norm like this, and we can check whether it is a norm or not by checking all the properties of a norm. Okay, so the question is it complete? So what am I doing? I am taking, so my question is it complete? So is it a Banach space? So I'm taking a sequence that is contained in this space, and I'm saying that Fn converges to some F as n goes to infinity. My question is, does this limit F belongs to the space? I need to check that this limit F is continuous. So if it is continuous, I'm done. So this definition implies that Fn minus F, the norm of Fn minus F is going to 0 as n goes to infinity. Yeah, because this means this. And how do we define norm? So Fn of x minus f of x in the maximum norm sense for all x from -1 to 1 goes to 0 as n goes to infinity. So this is true for all x in this domain, and each Fn of x is continuous. So according to this definition, Fn converges to F uniformly, because the above relation is true for all x pointwise. But since this pointwise is in the sense of maximum and the norm, then this condition implies that, okay, this convergence is uniform. And there is a result in basic analysis that if your Fn are continuous, each Fn is continuous, and they converge to some F uniformly, then that F must be continuous. So there are two versions of the theorem. If you read analysis, the basic analysis, each Fn is continuous and they converge uniformly to a function F, then F must be continuous. Excuse me. And the second result is each Fn is continuous, they converge to some F is also continuous, then this convergence is uniform. These are two results. So we are applying one of these. Yeah, so this tells that f is continuous. If f is continuous, it means f belongs to the Banach space. What does it mean? It means X is a Banach space. Excuse me. So I've taken an example and showed that it is a Banach space by using some sort of convergence results. Okay, let us take another example and see that whether it is a Banach space or not. So X, which is a set of polynomials from -1 to 1 to the set of real numbers. And what is P? P is a polynomial of certain fixed degree. So I take a sequence of polynomials that converge to some f uniformly. My question is f a polynomial? So it is sometimes really hard to check that, okay, whether this is true or not. But if you are going to provide one counter example, then you are done. You don't need to do anything else. So I'm taking a sequence that starts from 1. P1 is x, P2 is, P1 is 1 plus x, P2 is 1 plus x square over 2 factorial. So I can define my Pn to be sum I is equal to 1 to n x to the I over I factorial. So this is my sequence, and each of these is a polynomial. So what is going to be the limit of these Pn? So limit n goes to infinity of Pn is sum, sorry, should be over here, sum I equals 1 to n x to the I over I factorial, but this is not n, this is now infinity because I have applied the limit, and you know very well this is sequence for e to the x, but this does not belong to the set of polynomials that we have discussed so far. So or this does not belong to the space that we have defined so far. So the space that I've given in this example is not a Banach space. So this is a Banach space and this is not a Banach space. Okay, so the next example that I have is really very famous example, that is small LP, or what we call P summable spaces, where P is between 1 and less than infinity, which is set of some sequences, and the elements in the sequence is A1, A2, and so on, an plus 1, and this is going to be infinite, such that you take each term in the sequence, take it to power p, take their sum from 1 to infinity is always finite. And if I take any element in this space, let's say this is the element n is equal to 1 to infinity. So this space contains the sequences. So sequence contains elements infinite, and this space contains many examples of such sequences. So the norm of this sequence is defined to be, the LP norm is defined to be AI to the P, and sum over I equals 1 to infinity to 1 over P. And you can simply check that this is also a norm. So we can check that LP is Banach space, and it's really simple. We have to take a sequence AI, or simply let's say AJ, from 1 to infinity, that converges to some A tilde. So this should be from n is equal to 1 to infinity, and this is n is equal to 1 to infinity. So this is the index for the terms in the sequence, but this AJ shows multiple of such sequences, and this sequence of sequences converges to A tilde, which is one sequence. So a sequence of sequences converges to a single sequence. Okay, so how can you show that the norm of the limit that we have so far, this limit is finite? So this can be checked easily. I'm not going to do it. So, but let me give you some sort of short hint that we have to show this thing that okay, A tilde from 1 to infinity is finite. I can apply triangle inequality or some sort of Minkowski's inequality. If you know, otherwise we'll discuss. Then I can subtract some an to the p, and I can also add those n's to the p. Now n is some sort of large number. N belongs to natural numbers. And what about this difference? Is this difference? So we know very well that A tilde is some sort of limit of a sequence an. So this thing must be smaller than some epsilon, because this is how you define the convergence. Like this goes to zero as big N goes to infinity. And you can also show that okay, this thing is finite. Why it is finite? Because this is like LP norm of ANs, which are the sequences in the space. So this should be finite. So this whole thing is less than infinity. What does it imply? It implies that okay, this A tilde, it belongs to Banach space. So it implies A tilde n is equal to 1 to infinity belongs to the space that I've defined so far. It implies LP is a Banach space for P 1 in infinity. Okay, so these are maybe a few examples of Banach spaces, and maybe we'll need a couple of these, and maybe we won't need any of these when we are going to discuss uh, partial differential equations. So I have very famous result. Now, what do we call a contraction map? So xy are normed linear spaces. I have a mapping T from x to y is called a contraction map if there exists theta between 0 and 1 such that tx minus ty in y norm is less than or equal to theta times x minus y in x norm for all xy from the non-linear space that we have. So the main idea is when you operate t on x and y and take their difference and take their norm in y, it is always bounded by some theta times norm of x minus y in x. So you are going to operate t on x minus x and y. It is always bounded by the difference between x and y times some contraction factor, which is going to be theta, which is less than 1. This map is really important because of Banach fixed point theorem. So let me state the theorem. So Banach fixed point theorem. The theorem says that X is a Banach space. T is a mapping from X to itself that we can show in this way, is a contraction map. So T is a contraction map. Then T has a unique fixed point X star that also belongs to the space that we have taken so far. So this is X star and this is space X. So it means that T of X star is same as X star. So like if I have a function, if I substitute X and if I get same result back X, then I call that, okay, X is going to be the fixed point of this map. Similarly, X star is going to be a fixed point here. Furthermore, for all y in X, if I take any y from the space and I operate t k times to that y, then I take limit as k goes to infinity, then what happens? Okay, so it means that limit k goes to infinity. What I do, I apply t to y, which becomes y again. Then I apply t again, t of y, which becomes y. So this is like if you apply map infinitely many times, you get again the same thing. Yeah, this is going to be some sort of convergence map, and it will always converge to the fixed point that you have. So if you keep on applying, it will always converge to the fixed point that you have for all y in X. So if you take this means that if you take any element from the space and you keep on applying the contraction, the contraction map, it will automatically return you the fixed point at the end, and it will never go beyond the fixed point. I have another definition. We'll be applying these results quite often in the study of partial differential equations. So the definition is X and Y are normed linear spaces. T from X to Y is bounded if, so I say that an operator T is an operator from X to Y, is bounded if the norm of T, which is defined to be operate T on X and take their norm in Y and norm of X in X and take their supremum for all X in X, but those whose norm, those who are not itself 0 is going to be finite. So the norm of T, which I have defined in this way, should be finite. Or in other words, I can say that, okay, Tx in Y norm should be bounded by some C0 norm of X in X. Then I can say that this C0 must be at least as big as norm of T. So like the minimum of these constants, the minimum value of these constants is referred as the norm of the operator T. So you collect all those constants and take the minimum value. This is going to be the norm of operator T. Okay, then I have a very famous result, maybe very crucial. It's maybe a theorem. It says that X is normed linear space and X is finite dimensional, then the result is if T is linear, then T is continuous and vice versa. So T linear implies T continuous and T continuous implies T linear. So I have T to be a linear operator. To be an operator, if I'm in finite dimensional spaces, then if T is linear, then it implies that T is continuous. If the operator T is continuous, it implies that operator T is linear. We'll discuss what do you mean by linearity is simple, everyone knows. We'll discuss what do you mean by continuity of an operator. And then like we have defined what do you mean by an operator to be bounded. And I can just quote the same result, but with a with a with a little modification, that now X is non-linear spaces and this X is infinite dimensional. Then if T is linear plus bounded. So in infinite dimensional spaces, we need T to be bounded so that we get T to be a continuous map. So this is some sort of extra thing that we need. Now I have another definition, which is really a crucial definition, what we call the definition of dual spaces. So dual spaces. So again, I have X to be a non-linear space. We define the dual space of X, the dual space of X, which I named to be X star, is the set of all linear plus bounded functionals on X. So like X star is a map of all those functions from X to R which are linear and bounded. So F is linear plus bounded. And if some functional that belongs to X star, then its norm in X star, because X star is the dual space that contains all the linear operators or linear maps, then its norm is defined as take f of X divided by norm of X in X and take their supremum for all X in X and where X is not equal to 0. And for all X in X, I can say that this f of X is also written as f operated on X, or this is some sort of, this is not inner product, this is an operator f which is acting on X from the space. And this is always a real number because this is how we define functionals. You know very well in definition, the codomain set is a set of real numbers. You can also say this thing, okay, if I operate f on X, I get a real number, and norm on real number is simply some sort of absolute value, nothing else. So this thing is referred as action of f on X. Action of f on X. I have a little theorem that X star is a Banach space. This is a really crucial thing. You take X to be a Banach space or not, but X star, the dual space, is always a Banach space. And there's a simple reasoning behind it, that the dual space is a space that takes element from the space and maps them to real numbers. So the output is a real number, and real number set is complete. It is a Banach space, so it implies that, okay, X star is also a Banach space. But there is going to be a rigorous proof behind these all the things, but this is simply beyond the scope of this course. I will definitely offer some courses on function analysis and measure theory separately. Then over there we can discuss these all the things in detail. I have another definition which we call adjoint operator. So I have x, y are Banach spaces. T is a map which is linear. D adjoint operator. So what is adjoint operator? It's some sort of operator T star which is mapped from Y star to X star such that what is true? For all G in Y star, X in X, such that T star G operated on X is same as G T operated on X. So the simple thing to keep these things in mind is, okay, you have T star and you take it over there, this becomes, you take it on the side, this becomes T. But this is not that much simple. So let me give you an idea. This G is an element in Y star. So T star takes an element from Y star and maps them to X star. So let me tell you, this whole element is in X star and this is the element is in X. So an element in X star is acting on an element in X on the left-hand side. True. Let us go to the right-hand side. G is an element in Y star, and you know very well this X is an element in X, but Tx is an element in Y. So this is an element in Y. So on the left-hand side, X star is acting on X. On the right-hand side, Y star is acting on Y. Makes sense. So if this relation holds, then we say that, okay, this is some sort of adjoint operator. One of the example that motivates us is Laplacian operator, which is C2 periodic to C0 periodic. So Laplacian operator always demands that, okay, give me a function which is at least C2. It means it is continuous and its at least two derivatives are also continuous. Periodic is some sort of extension. Okay, the functions, give me the functions which are periodic. Okay. The Laplacian will give you an output. It will give you a function which is C0, means it is continuous at least. And the result is also going to be periodic. Okay, so in this space, how do you define the action? The action in this C2 spaces is defined as f times g dx, the integral of fg dx. And if I take uv from C2 periodic, if I take two functions from C2 periodic, then what can I do? I can take Laplacian of, what can I do? I can take Laplacian of u acting on v is same as integral of Laplacian of u times v dx. And now if I integrate by parts this thing twice, then the Laplacian is transferred to v. So this is some sort of technical detail. I can tell you right now, but I will tell you when we'll discuss these Green's identities and the corresponding results. And let me squeeze it a bit. So u Laplacian of v dx, and you know very well I can write it u Laplacian of v. So you know very well that, okay, at this place, there should be Laplacian star. So if this is Laplacian star, this is Laplacian, but Laplacian star is same as Laplacian. So we say that what is the adjoint operator of Laplace is Laplace star, but both are same. This type of operator is called self-adjoint operator. So Laplacian C2 periodic is a self-adjoint operator. What do you mean by that? The adjoint of Laplacian is Laplacian same. We'll study these things in detail. What do you mean by how you are going to integrate? What do you mean by these spaces when we are going to discuss some advanced things? Oh, really sorry. Okay. Definition. The next definition is, it's really a crucial definition. So X is a Banach space. X star is its dual space. So the first thing that I'm going to discuss is called strong convergence. This is really crucial thing when we want to study partial differential equations in detail. So if I take a sequence xn that belongs to X, we say this sequence converges to a limit X strongly if what happens, xn minus x in the sense of norm in X goes to 0 as n goes to infinity. This also implies that the norm of xn in X converges to norm of X in X. But the other way around is not always true. We'll look into different examples of these things as well. But mainly the definition of a strong convergence is this. So you take a sequence and you take its limit. Their difference in the sense of norm should go to 0 as n goes to infinity. The next thing is weak convergence. So these are the main results that we are going to discuss. We'll definitely apply these results in the practical things that we'll do. So we say xn converges to X weakly. So I write W weakly if for all y and x star. So I'm taking y and x star. X star is a dual space. So y is going to be an operator. Y on operated on xn converges to y operated on x. So this is what we call weak convergence as n goes to infinity. Or in other words, y of xn converges to y of x as n goes to infinity. This is how we define weak convergence. The third notion is, what do we call weak star convergence or weakly star convergence, depends how you call it. Weak star convergence. What is weak star convergence? So this is simply the convergence of operators. So I take a sequence of operators in X star, and we say yn converges to some y in weak star sense if for all x in X, yn acting on X converges to y acting on X as n goes to infinity. This is going to be the definition, or you can rewrite this thing as yn acting on X converges to y acting on X as n goes to infinity. So this is how we define these things. Okay, so these are three real important things. What do you mean by strong convergence and weak star convergence? I think the lecture is going to be a little longer, but I'm going to end it after maybe 5 or 10 minutes. I think it won't take that much long. Let me define one thing. So I'm going to define what do we mean by inner product. So I have X, which is linear space. I have a map which takes two entries from the space and maps them to R, is a scalar product. We call this map a scalar product, also called inner product. So better to write inner product. Inner product. If what happens, number one, the relationship is symmetric for all x, y, and x. So the usual inner product on R or R2 is symmetric. You know very well that thing. So, but this is going to be general definition, and it is linear in both components. So I'm going to write maybe for the first component lambda1 x1 plus lambda2 x2 operated on y is same as lambda1 x1 operated on y plus lambda2 x2 operated on y for all lambda1 lambda2 in R. And third property is the inner product between the similar elements is going to be always non-negative. Using this inner product, I can define something else. So X is linear space with a scalar product or inner product is called an inner product space. So if I define some sort of space and I'm giving it the notion of inner product, then I call it inner product space, also called IPS in short, inner product space. And with respect to some sort of inner product, but I can also assign a norm to it, and that norm, how does the norm look like? The norm is square root of x, inner product of x with x. And I have one thing else. If inner product, no, just write complete inner product spaces are called Hilbert spaces. So if the space is complete, the inner product space is complete, we call it a Hilbert space. And we have some of the properties for the norm which comes from the inner product. We had other norms which we discussed in Banach spaces and normed spaces, but these are the norms which come from the inner product, and that satisfy some properties like the absolute value of the inner product between x and y is bounded by norm of x and norm of y. This is Cauchy-Schwarz. We'll look into this property as well. X plus y is less than or equal to norm of x plus norm of y. This is the triangle inequality. So a norm that gives the unit product space and Hilbert space must satisfy these properties. Maybe you won't find these properties in other norms. Maybe you can find the second one, but not the first one, because you don't have notion of inner product over there. You have notion of inner product over here. And you won't find third one in general, but if you find third one, and that's going to be the normed space. That's going to be the inner product space. So this is called the, I think, parallelogram law. So these are some of the properties which are related to inner product spaces and Hilbert spaces. So these are like main chunks of the theorems that we needed to discuss when we are going to discuss function analysis, and we'll apply these results when we are going to study many advanced results. So let me tell you what things are really important. The really important thing is a Banach space, and it is some sort of a complete space. And separability or density properties are really important. These three examples that we have discussed so far, 1, 2, and 3, are crucial examples. Then we'll discuss other examples of integrable spaces as well when we are going to discuss Sobolev spaces. Contraction map, okay, but then the norm of an operator, and dual space is a really very important notion. And X star is a Banach, the dual spaces are always Banach spaces. This example is really crucial example when we study function analysis, not function analysis, but PDEs. And the most important thing for this lecture is going to be strong convergence, and weak star convergence. Then we'll discuss in detail what do you mean by Hilbert spaces, and we'll discuss maybe many more examples of Hilbert spaces as well. So this is going to be the end of lecture 1. In lecture 2, I'll be revising some of the basic and major results in measure theory. And one of the main result is going to be monotone convergence theorem, or another version is like Lebesgue dominated convergence theorem, which is really important when we are going to discuss integrations and differentiations. These things are really important. So till then, goodbye, and see you in the very next lecture very soon.